Today I thought I'd talk about methane and the shape of carbon, because it's something that we all take for granted. But once upon a time, nobody had any idea what the shapes the carbon would adopt would be. So it's been known for a long time now that 4-coordinate carbon, so that's carbon with 4 bonds, would form what we call a tetrahedral shape. So this is a tetrahedral shape here. And actually 100 years before I was born, a guy called Van 't Hoff proposed this, and this was revolutionary at the time. And this became a real cornerstone of chemistry. If you say 4-coordinate carbon to people, they'll immediately think it's a tetrahedral shape like this. And it wasn't until actually around about the time I was born, nearly 100 years later, that a Nobel Prize-winning chemist called Hoffman said, but what if it was flat and square? And nobody had really taken this seriously until then. And he did lots of calculations, and he found the reason for this, that you don't have this form, is because this form is much more unstable compared to this form here. But chemists don't like it when they're told that a molecule isn't viable because it's too unstable. So this made people start to think about, well, how could we crack a molecule like this? And a few years later, a guy called von Schleyer said, well, what happens if we take this molecule and we take 2 of those hydrogens off and replace them with lithiums? Does that make it any more stable? And the answer was, well, possibly yes, but maybe not in this form where the lithiums are opposite each other. And what he worked out is that if you take a slightly different form where they're next to each other, it actually becomes much more feasible as a target to try and attempt to crack. So this was quite tricky to do. So what people decided to do was to change these hydrogens into other groups, and then this would help us to isolate individual methane molecules. And one way to do that is to use phosphorus. And that's because phosphorus can have other groups appended to it, and then you can try and trap an individual molecule. So then we go for a bit of a leap from this to, which is what we've actually managed to do recently, which is this. As you can see, there's quite a difference here. So what this molecule is that's a lithium there. Here's your phosphorus center, and there's the other one. And these have got big, nice, bulky benzene rings on them, so this helps to keep the whole molecule as an individual rather than grouping together with its mates. And each phosphorus has a nitrogen on it which grabs this lithium and pins it in place. So what you can see is you've got a central carbon here, so that's your methane carbon right there, and there's a lithium there, and a phosphorus and a phosphorus. And the point is it's nearly planar. If you look at it from the side, you can see the lithium's a little bit above from where the 2 phosphorus centers are, but it's really, really close. And there's a few examples in the literature now where people have made these compounds where carbon has 4 bonds, but it's planar or really close. And this is really exciting because it helps to validate the calculations which predicted these molecules. And it's really satisfying as well because, like I said, we hate being told that we can't make molecules. So what we're really, we've pretty much got to nowadays is we've started with a carbon like this, and now we can pretty much make it do this. We've just had this published in a journal called Angewandte, which is a good journal to be published in. So hopefully now everybody in the chemical world will get to see what we've done. Now we're going to go into the lab, because seeing this model is all very well and fine, but I think you should actually get to see what this compound looks like. Okay, so this is Ollie. He's just come into the end of his first year of his PhD, and he's the guy who made this compound.
And he's going to show it to us, is he?
Yeah, he is.
Alright.
So this compound, like most of the things we make, it wouldn't exist out on a bench in the air, so we have to handle it under nitrogen. It's perfectly stable under nitrogen, just you have to have it under nitrogen. So we've got this glove box, which is full of dry nitrogen, so it can be handled in there as if it were out on the bench. So Ollie's just going to put his hands into the gloves, and then he's going to just pick some out and weigh it out into a boat so you can actually see it.
Why is it so important to you to make this planar molecule? You're just doing it for the sake of it.
Yeah, there's nothing wrong with that. It's expanding knowledge, improving our knowledge. This doesn't have to have an actual use. The point is, if you have predictions, it's nice to be able to validate them, because that helps to validate the actual theory that was used to make the prediction. But it just pushes out the boundaries of what we know to be possible and makes us be a bit more daring about what we try next.